Let's talk about conversion from a composition by mass to a molar composition. So from your textbook, this is example 3.3-3, and we're calling it example 3.3 within your notes. You have an example above this related to conversions of mass and mole fractions, which is going to be example 3.2, and we're going to do that in class. So we're going to start out with a mixture of gases that have the following composition by mass. And the fact that it's by mass is really important here. So we're told that we have gases of oxygen, carbon monoxide, CO2, nitrogen gas, and we're told these kind of percents by composition, right? And the percent by mass. So if it's percent by mass, that means of a total system, you would have 16% oxygen. So if x is a fraction, right, everything with an x has to sum up to 1. So in this case, we represent things in decimal form. So the composition, the mass fraction that is O2 is 0.16 grams of O2 per gram of total, because all of these x's should add up to 1 because it's a mass fraction. So they should all be less than 1, but the total composition should add up to 1. So if we go through, we can do this for every single one of these. We can say, okay, well, if we have CO, carbon monoxide, and it's 4% by composition, that means it's 0.04 grams of CO per gram. And I just want you to take a look at the units really quick because this is really important. It's grams of the compound per gram total. And that's really critical because it looks like the units would cancel gram per gram, right? But it's grams of something per gram of the total substance. And that's a good thing to keep writing in your problems as you start to make sure that you really understand this concept here. So we have mass composition, but we want to go to molar composition. So if X is mass fraction, we want to go to Y, which is mole fraction here. Okay, so that's the ultimate thing we're trying to do. We're trying to go from X to Y. Sorry, we went off the page for a second there. All right, so let's talk about that. So I think in this type of problem, one thing that I like to do is I like to set up a table. I find it much easier for myself to kind of understand what's going on. So I set that table up again and I said, okay, here's my components. Here are my 4 gases. Here's the mass fraction, right? This is in something of grams per gram, which means that if we had 100 grams of that substance, which is a common basis of calculation that we're going to assume, then we'd have 16 grams out of 100, right, would still give us the 0.16. If we had 4 grams out of 100, we'd still get the 0.04 grams per gram total. So sometimes this is a nice way to go from gram per gram total to a total number of grams in the system. So sometimes we assume this 100 grams as like a basis of calculation. So this is your total down here, and all these numbers add up to 100. And the reason that we like to do that is this is now in terms of just grams of the substance, which means that we can do things with it. So there, you can't go straight from a mass fraction to a mole fraction without going through the molecular weight. This is really critical. Molecular weight, you can't multiply by just the mass fraction because the mass fraction is in terms of grams of substance per gram of total. You need to start with the grams of the substance, and that's what this column with the M is representing. So you have to come here first, and then you can multiply by the molecular weight because the molecular weight is specific to each compound. It's not the same as the total, right? So I've put in the molecular weights already. If you forget how to get molecular weights, remember that they come from the periodic table, and this is in grams per mole. So now we can start to move forward. So I have a little formula down here for those of you who like formulas. I normally look at units to figure out how to get moles, but if it's helpful, remember that if you take a mass of a substance and divide it by its molecular weight, you're going to get the moles of a substance. And that's just unit analysis. Mass is in terms of grams, and molecular weight is in terms of grams per mole. So if we divide grams by grams per mole, you get moles here. So let's do that, right? So we've got mass, we've got molecular weight. Now let's go and grab the number of moles. There we go. Let's center that up on the page for you. All right. So if I take mass divided by molecular weight, for oxygen, I'm going to get 0.5 moles. For carbon monoxide, I'm going to get 0.14. For carbon dioxide, I'm going to get 0.39. And then for nitrogen gas, I'm going to get 2.20. So check my math. If you're not sure how we got those numbers, I'm taking the mass and dividing it by the molecular weight. Okay. Now, the reason that we need the number of moles is that if you remember, a mole fraction is the number of moles per mole total. So just like a mass fraction, you need this mole total in order to figure out what percent basically these make up. So what we need to do is we need to add all of these numbers up to find out what our total is. So our total, if we add those up, is going to be 3.28. So I have a little formula down here. If you're somebody who prefers formula, your mole fraction is the moles of the species, right? So one of those rows divided by that total number, that 3.28. So if I go through and I divide each of these numbers by 3.28, I'm going to get 0.15 for oxygen, 0.04 for carbon monoxide, 0.12 for carbon dioxide, and 0.69 for nitrogen. And you'll notice those numbers, they're not the same as the mass fraction, right? They're pretty close in this instance, right? We're looking at the composition of air. Excuse me. But they're not the same. And that's really, really critical, right? So we can't hop straight from X over to Y. We can't assume that they're the same because every species has a different molecular weight. So I personally like to use this table method when it comes to changing between mole composition and mass composition. When we say the word composition, we're looking at fractions, right? So if you have a mass fraction, you need to find a mass by assuming that you have 100 grams of a species. You need to know the molecular weight of each species, find the number of moles using that molecular weight, take the total so that you can get over to that mole fraction. So we're going to see an example very similar to this in class. This is a really key concept to be able to do in this particular class.